Okay, so today I'm going to partially talk about the model-free prediction and also partially about the model-free control. So first of all, the difference between prediction and control is that for prediction, you you are given a policy and an MDP, an environment. Like it doesn't matter whether it is a known MDP or an unknown MDP. So every environment has an MDP. So if we know everything about the MDP, then we can solve it by the dynamic programming. While in the other case, we can't. So we have to rely on sampling methods such as which is basically model-free methods instead of model-based. So first of all, so in terms of model-free prediction, the prediction is that we're given a policy. So we are evaluating that policy. While for the control part, we do not evaluate a particular policy, but we try to figure out what's the optimal policy among the policy that we have at that point. So if you think as a, so basically the control part is an extension of the prediction part. And if you think it as a double for loop, the inner loop would be the prediction part, because we're in the inner loop, we have to calculate all the values, estimation of values per policy, and in the outer for loop, then we can just choose the either the maximum or which by such some criteria we can figure out the most optimal one. That's the idea. And okay, so in terms of the model-free prediction, since now we don't know everything about the environment, we can't use the dynamic programming. So we have to rely on sampling methods, which is instead of using some kind of since now we don't know the mechanism, which is the state transition function or the reward function, we can't plan. Now we actually have to, the agent actually has to make an action and get the feedback from the environment, and based on the feedback, update the value estimation or either the action value estimation, and then greedily or based on some policy, you can just improve the value estimations. So the difference between the Monte Carlo method and the temporal difference learning is that for Monte Carlo method, it's basically, so first of all, we know that the concept of an episode in a reinforcement learning setting is that from the start of, for example, an agent, if there's a robot, the start of the episode would be when the robot is start moving, and the end of the episode is when the robot hits some kind of a block, or anyway when it reaches its own termination step. So for the Monte Carlo method, it's basically we just sample one whole episode from the start to the end, and then we average the reward got from that specific episode, and then update our policy, which means that in this setting, we can't update our policy after a time step. We can only update the policy after when the whole episode ends, which means that in this case, since we are actually really interacting with the environment, there's low bias, because we are just changing our value function towards the actual interaction between the agent and the environment. But in this case, the variance is very high because there can be so many different, because there's no such estimation factor, and there can be so much variance across different episodes. While episode 1 leads to this trajectory, in episode 2 it could lead to a completely different trajectory. It all depends on the unknown MDP. So there's so much possibility for variant to come in that situation. So in this case, however, the advantage of the Monte Carlo update is that it can also be done incrementally especially for in non-stationary problems. It can be useful to track a running mean, which we can also forget the old episodes. So there can be, so for some problems, Monte Carlo method could be a good approach. The opposite of the Monte Carlo method in this case is the temporal difference learning, which is basically, it's still, now we add some estimation property instead of just actually sampling real returns. In this case, we still learn directly from the episodes of experience, but we can learn from incomplete episodes basically by bootstrapping. So for example, the temporal difference learning, we can first make an actual action as we did in the Monte Carlo method, but just restrict the range of actions into a certain threshold. After we make those actions, then in the time steps thereafter, we just use an estimation of the reward. So you can think of it as basically the temporal difference learning updating a guess towards a guess. And also note that as for Monte Carlo method, it doesn't require any knowledge of the MDP transition or rewards, which is basically means that it's a model-free approach. So the problem of the temporal difference learning is that now it has much less variance because now there's much less randomness in terms of actual variable perspective. However, it does have an advantage over Monte Carlo method in terms of bias. So it's usually more efficient than Monte Carlo method because we don't really have to wait until a whole episode to end. And also it is given that even this temporal difference method relies a lot on the estimation, it still converges to the optimal policy because we do make actual action, which makes this algorithm still grounded to the truth. But since this method is based on bootstrapping, it naturally is more sensitive to the initial value because the trajectories can differ depending on which initial state we started. So basically to compromise between these two methods, the temporal difference learning and the Monte Carlo method, you can think there was a modification of this too, which is basically called the n-step TD learning. So if you think it as the Monte Carlo method, just trying out an episode, which is the real interaction with the environment, until time step of n, 1 to n. While for the temporal difference learning, the generic one, just making one actual interaction and then relying the rest on some estimation. So this n-step TD learning, temporal difference learning, is instead of just making one actual interaction, extending the number of interactions into some kind of hyperparameter, which is n. So here there's so by doing this, the advantage is that now since we are actually, we don't have to wait until the end of the episode, while we can still update the policy online while we are trying out, like while we are trying out the episode itself. But the problem of this approach is that because the n is a hyperparameter, it is very difficult to figure out the optimal n. And given the nature of reinforcement learning, it is doing a grid search would be very computationally expensive. So and also the results, especially for random walk examples, the results greatly vary by n, which gives the importance of figuring out a way to incorporate all the n's. The most simple version of it would be averaging out between the two-step TD learning and the four-step TD learning. So it's basically just getting the expected value of those two returns. But this is just getting the arithmetic mean of this returns is a very naive approach. So instead of doing that, we basically introduce a concept of a lambda, which is confined between 0 and 1. And basically the lambda here means how much the importance of the steps in terms of updates are decayed by advancing time step. And the way this formula is written is basically getting the weighted average of the n steps. Still the n step is an hyperparameter, but now, like for example, if we say that the length, the total time step of the episode is 30, then if we choose the hyperparameter n as 10, then until 10, the weights for each time step will be calculated by the TD lambda formula, but afterwards from 10 to 30, the leftovers will be just aggregated into one sum. So we could account for the leftovers as well. And when it comes to the TD lambda approach, there's two implementations, which is the forward view TD lambda and the backward view TD lambda, which means that the forward view, as the term itself suggests, it looks into the future to compute the return, which naturally leads to a disadvantage which we had for the Monte Carlo method, because we have to, as I just said, since we have to put into account for the leftovers, which exceeds the value of n in the total episode, now we have to wait until the episode ends. Then when it ends, then after we can calculate the returns based on the lambda. So to compensate for that disadvantage, a backward view TD lambda was introduced, which basically uses the eligibility traces. So the idea is, instead of looking forward and giving a weighted average to each time step and updating based upon that, now we rely on the backward, like for example, at time step t, we don't consider time step t1, t2, and so on. We now rely on t minus 2, like the past. And the way it's done is basically introducing two heuristic, which is the frequency heuristic which we assign a credit to the most frequent states. And the other one is the recency heuristic, which assigns credit to the most recent states. And per state, there will be an calculation. These two states combined, it will be called an eligibility trace. And per state, these eligibility traces are calculated. And when it comes to an update, when a TD error is identified, then instead of just updating the value based upon the learning rate and the TD error, now we also multiply it by the eligibility trace. So the basic idea is that for a particular update, TD error which leads to an update, which states contributed the most? So which states we do it, should we give most credit in terms of this specific update? So that's the main reason why we are telescoping to the backwardly. And the advantage is obviously that since we don't have to wait until the episode ends, we can just apply this to incomplete sequences while it's continuing. And also that the way the eligibility trace is calculated is based on the lambda, which can be reproduced across different time steps. So we do not have to, it's not computationally challenging because we can just use the same lambda value for, in terms of keeping track for all states eligibility values. So that part was for the model-free prediction. And so to refresh, the model-free prediction is basically evaluating the value of a particular policy, while the model-free control is trying to figure out the optimal policy given the pool of available policies. And also emphasize that it's a model-free environment, which means that we don't know the state transition or reward function of the MDP. It's an unknown MDP, so we have to actually sample instead of actually doing such stuff as bootstrapping. So when it comes to model-free control, there are two types of learning, which is on-policy learning and off-policy learning. So the basic idea of the on-policy learning is that one specific policy is governing the action selection policy and the update policy. So we are basically trying to learn about a specific policy, and a specific policy also determines which sample we will learn on in the future. Because in terms of reinforcement learning, given the sequential nature of the reinforcement learning itself, unlike supervised or unsupervised learning, the current current policy we're relying on determines the next experience that we'll get from the environment. So that was for the on-policy learning. And for the off-policy learning, it's basically a robot. Like if there's two robots in a space, one robot is learning with its own policy after observing another robot moving around with that robot also has its own policy. So now there's two separate policies, which is basically meaning that the update policy and the action selection policy are different. So the disadvantage of the on-policy learning is basically that it's very easy to get stuck into some local minima because it's just reinforcing its experiment to based on the sequence that it observed. So instead of exploring new, instead of trying to aim to get long-term benefits, it's just only greedily searching for the short-term benefits, which would unlikely lead to the global optimum. While for the off-policy learning, since you can differentiate between the update policy and the action selection policy, you could, for the action selection policy, you could introduce some exploration factor instead of just sticking to some direction that's greedy direction. So the off-policy learning is more of an extension on the on-policy learning, which is used much more. So for off-policy learning, so the most in terms of, so now it's again the exploration and exploitation issue, which exploration should be guaranteed to some extent. Exploration is needed to ensure that the agent is really putting every state into account in terms of his own update of its value estimation of the environment. And the most simplest idea for ensuring such continuous exploration is the epsilon greedy exploration, which is basically this epsilon is for a probability, which is for choosing an action at random instead of just sticking to some greedy action, which this naturally means enables the exploration and aiming for the long-term benefits. And with probability 1 minus epsilon, obviously it will always choose the greedy action. So when it comes to the generalized policy iteration, when we implement, so the generalized policy iteration is basically composed of two directions. So we're alternating between two processes, which is the policy evaluation, which is obviously getting the value function, calculating the return for a specific policy, and based on, and that will lead to the update of the value function, and on top of that, there will have policy improvement would happen. But when it comes to the model-free control, unlike the model-based control, we cannot use the value function. We instead have to use the action value function. And the reason for it is that when we use the state value function for update, since we only have the values per state, we need a model to estimate, to guess, to plan which action would be the best for our criteria. If we're only given states, then we can't really make any greedy action, because action is can't be determined by only the state information. So instead of using the state value function, we have to rely on the action value function. So in this case, we don't need any model, which enables model-free control. So for model-free control, the action value function, which is a Q function, Q value should be used. And when it comes to the, so for the general policy iteration, which is alternating between these two processes of policy evaluation, policy improvement, now we could implement the Monte Carlo method into this policy iteration. And specifically now in the Monte Carlo policy iteration, for the policy evaluation, we use the Monte Carlo method on the Q value. And for the policy improvement, we now use the epsilon greedy policy improvement. But the thing is that, as we have seen for the value iteration in the dynamic programming part, it's unnecessary to update the value multiple times per a value function, per original value function. So because of the theorem that for any epsilon greedy policy, if we choose at least one action greedily, the whole policy set, which is the policy is a set of actions, will be at least the same or greater than the policy based on the old value function will improve. So we really don't have to try out multiple episodes per one update of the value function. We could just more frequently after one episode, we could just update the Q value function, and then instead of trying out multiple times, we could just right away try out a new episode based on that, and so on. And this would more rapidly converge to the optimal Q and the optimal policy.